Hello again. So this section is about potential energy. So for potential energy, we're looking at stored energy. Okay. So oftentimes when we think of stored energy, we think of like food or things like that. But specifically in physics, we have two main types of stored energy. So one is from gravity. So for example, if I have a book, if I hold a book up like this, it has potential to fall, right? So it has potential to cause the book to move. The other type of potential energy that we'll be talking about is spring potential. So if I have a rubber band, if I pull it, it also has the potential to move. Now remember, in physics, when we're talking about energy, we're talking about pain, okay? So if I have more energy, that means it will be more painful. So I want you to imagine you are sitting down right here, and I'm holding this book above your head. What are the two ways that I can make it more painful if I dropped it on your head? Okay? What are the two different ways that that could change? Okay, yes. So there's two ways. One would be the mass. Okay? If I get two books, that will be more painful than just one book, right? Or if I get a bowling ball, right? Heavier will mean more painful. The other way would be what? If I lift it up high, right? If it's nice and high, it's going to fall a long way. It's going to hurt more, right? So there are two things that this depends on, M and H. Now, can you think of a third way? Imagine this scenario. I have this textbook above your head. Is there a place where you would not be worried at all? You wouldn't be worried about it hitting you on the head. Think about, try to broaden your horizons. Think outside of the Earth. Yeah, in space it wouldn't matter. So what would be the third variable? The third variable is G. Okay? So potential energy from gravity, PEG, is equal to mgh. So it's dependent on the mass, gravity itself, and then the height. Okay? Potential energy is just stored energy. Okay? So let's go ahead and keep moving. So the second type of energy we're going to talk about is elastic potential energy, or energy from a spring. Okay? So in this case, what we're thinking about is I have a rubber band, okay? And you're right here, I'm gonna pull it back, right? When do you get worried? Or what are the different factors that would cause you to be concerned that it might hurt a lot, right? So one would be what? Yes, how far I stretch, so X, right? And what would be the second thing? What could I change about this that would make it more painful? Right? How strong the spring is. So if I had this big, massive spring, and barely pull back, it's going to hurt if it hits you, right? So that would be K. Okay? So the spring constant, and then also how far I stretch. Remember, we've already talked about relaxed length. At the relaxed length, it must have zero potential energy, right? Because it can't move without me starting to pull on it. Once I start pulling on it, now it can move. So remember, this X is distance past relaxed. Okay? So our formula is PES. I usually use S for spring. Sometimes you'll see it as an E, and it equals 1/2 kx squared. So the distance ends up being more important. Okay? We'll see a little bit more about why we have this half and the squared. But one thing to note is, after you take calculus, if you see a squared here, you often see a 1/2 here. Those two things often go together. So just like when we had our kinetic energy, 1/2 mv squared, we have a square here and a 1/2 here. Okay? So we already know what our spring constant is. That's how stretchy something is, right? So if it's very hard to stretch, the K value is very high. If it's very easy to stretch, the K value is very low. Okay, let's go ahead and look at our practice problems. Okay, so before we talk about this practice problem, we need to talk about mgh. So we have potential energy due to gravity is equal to mgh. Now, this h is a little bit interesting in that I can put h equals 0 anywhere. Okay, so we'll talk a little bit more about this idea when we're in class. But it's very interesting, in each individual problem, I can put it anywhere. So just how we talked about how our axes are flexible as long as we're not changing in the middle of a problem, same thing here. This is kind of like that similar idea. I can set h equal to 0 wherever I want, as long as I'm consistent in my problem, okay? But if the problem says relative to something, okay, this means h equals 0 at this spot. Okay, so if it says relative to the floor, well, that's going to be 0 for this problem. Okay, relative maybe to a table or something, that's going to be h equals 0. Okay, so class, we'll talk more about that. But let's go ahead and look at this question. So we have a 70 kg stuntman is attached to a bungee cord with an unstretched length of 15 meters. He jumps off a bridge spanning a river from a height of 50 meters. When he finally comes to a stop, the cord has a stretched length of 44 meters. Assuming the spring constant of the bungee cord is 71.8 newton meters, what is the total potential energy relative to the water when the man stops falling? So let's first of all just draw a picture just to help visualize this. So I got a bridge, so this is the guy, so he'll be here, okay, and then he's attached here. Now the water is here, so this distance here is 50, correct? From a height of 50. But this distance here is only what? Yeah, that distance is just 44. Okay, so that distance is just 44. So this distance is actually 6 meters. Okay, now what are the two types of energy that he will have at this point? Yeah, he has that spring potential energy because we have this bungee cord, but he also has what else? He also is above the ground, so he will also have gravitational potential energy. Mental note, he stops, so does he have kinetic energy? No, he won't have kinetic energy in this situation. So, my E total, so that's my total energy, is equal to PEG plus PES. So potential energy from gravity, potential energy from the spring. So let's go ahead and find this. Let's plug in my formula. Okay. As you can see, I wrote this statement out first and then I plugged in the formula. This is an important thing to learn how to do. This is how I'm going to expect you to do these types of problems, especially as it becomes more complicated. So on these problems below, I do want to see something like this if it's asking for like a total energy. I want to see you say, okay, I have the total energy is equal to these two things, then I'll plug in a formula for that. Okay? Okay, so this is equal to my mass, which is 70 times 10 times, what's its height? 6. Plus 1/2 times k, which is 71.8, times x squared, which is 44. Oh, okay, this is very important. It has an unstretched length of 15. So one way to do this, I need to subtract these two, right? So it'd be 44 minus 15 squared. Okay? So just do the calculation and use something, joules. Okay? If you want to plug it in, find it out, that's great, but I'm more concerned in this setup. These first 3 steps are what's really important. This calculation is not that important. Remember on the AP test, this would be probably a point, this would be a point, and then finally your answer would be like 1 point. So it's really important that you're getting that setup right, getting the final correct answer is not as important. So let's move on to our final question. Okay, so when a 2 kg mass is attached to a vertical spring, the spring is stretched 10 centimeters such that the mass is 50 centimeters above the table. What is the total potential energy associated with this mass relative to the table if the spring constant is 15 Newton meters? So this would look something like I have my table here, and then I have this spring suspended from something. I have a block here. Okay. So this would mean it's stretched. So this would be my x. Okay. So it's for this one I didn't need to subtract. And then I have this will be 10 cm. This here is 50 cm. Now remember, am I allowed to use centimeters for distance? No, not allowed. So I need to change this to 0.1 meter, 0.5 meters. Okay. So that's kind of the diagram there. Now remember, it says relative to the table. So h equals 0 here. Okay, so that is an important thing to know, relative to the table. So let's go ahead and set this problem up. So I get my E total is equal to, PEG plus PES. Okay? Sometimes you'll actually see, instead of an E or something else, you'll actually see a capital U. So U is also another variable to represent energy. So you could do like UG would be gravitational energy, or just U in general could be a total energy. So I have E total equals PEG. So the formula for that is mgh plus PES, which is 1/2 kx squared. So put an equal sign here. Let's go ahead and plug in. My mass is 2. 2 times 10 times my height is 0.5 plus 1/2 times k is 15. 0.1 squared. Then we solve that. Put it in your calculator. Get a number. Something joules. Okay. So this is sort of the basics where we're learning the different pieces. Okay. So this would be kind of like learning how to set up a free body diagram, learning how to set up an FNet, sort of a simpler FNet. But we're going to be able to start using this in the future. Okay. So let me know if you have any questions. There was a particular part of this that you really got stuck on. But next class, we're going to start taking this information and actually using it. So how can we actually calculate something? Like, why is this information important, right? So we've only learned, okay, how painful will something be if it hits you or if I put it above your head, right? In a second, we're going to say, okay, well now, if I drop this, can I find the velocity at the bottom? What are the relationships between the different types of energies? Okay? Right now, we're just learning the building blocks. So I will see you next class. Thanks for listening.